So you've come back to this video to learn about conjugated dienes and how they play a role in reaction theory and organic chemistry. And the reason is because delocalization is the culprit. So don't blame me for these reactions. You blame delocalization. I told you delocalization can make people go loco. And here is one of the ways that it can easily do that to the unsuspecting person. So let's say that we have just a simple, cute, little bitty molecule, CH2 double bond, CH single bond, CH double bond, CH2. Look how simple and innocent and sweet. Okay, well, let's add something that, other than HBr. Let's just add Cl2. All right, Cl2 with DCM. Hopefully you'll remember what happened with Cl2. Chlorine went on one and chlorine went on the other. So you would look at this reaction, and back in the day, you would look at this structure and you would be like, hey, I know what would happen. So I'm going to draw a structure, CH2. I'm just going to replicate what we started off with. Here, here, there, and there. And you would look at this and you would say, hey, listen, there's a double bond here and there's a double bond there. So I'm going to pick one of these double bonds. There's really no difference in them. So I'm just going to pick the one to the left. I'll erase it. And two sites of attachment open up here and here. So chlorine goes on one and chlorine goes on the other. And I would say, correct. Good job. Because that is a product. Well, some of you would target the ending on the right-hand side double bond, and you would do the same thing there. You would break that double bond, you would put a chlorine here and a chlorine there, and leave the one on the left alone. Well, if you did that, it would be the same molecule. Folks, there's no difference. It'd be the same molecule. Do you want me to prove it to you? I will. Look, CH2, double bond, CH, CH, double bond, CH2. So we're going to break the double bond. There we go. And two sides of attachment open up. And chlorine here and chlorine there. Do you remember how we named them? I hope so. What were the rules of nomenclature of alkenes? Well, we start toward the end of the alkene bond. If that's how we're going to name it, that's the priority group that we're going to give it. So the longest carbon chain, 1, 2, 3, 4. This is a butene. And this is a 1-butene because here's my number 1 carbon. That's the preference. I'm naming it as an ene. I give that the preference number. So carbon 1, carbon 2, carbon 3, and carbon 4. So on 3 and 4, I have a dichloro 1-butene. Okay, well, let's name this one over here to the right-hand side. What would its name be? Same rules, longest carbon chain, 1, 2, 3, 4, bute. On carbon 1, there's my double bond, 1-butene. And then on carbon 3 and carbon 4, I have dichloro, don't I? So this name is actually the same for both of these molecules, which proves, or helps prove, that they are identical. So whichever way that you go with this, it does not matter, folks. You're going to give me one answer or the other, and they're both actually the same answer. This is the answer that you would have given me. And I would have given you a check mark, because that is correct. It only says Cl2 and DCM. It doesn't say excess. It just says 1 mole, basically, of chlorine in methylene chloride as the solvent. But, this is not the only product. And now you're going to scream. And now you're going to throw things. And now you're going to slam your book and you're going to kick it off the desk. And you're going to probably kick your feet up in the air and say, why me, why me, why me? This is why it's not the only product. I'm going to redraw the starting reagent like I normally do. And this is what we started with. And what have we just talked about? We have spent video after video after video talking about Delocalization. Do you remember the rules of delocalization? Number 1, a pi can move toward a positive. Well, that doesn't apply here. Rule number 2, a pi can move toward a pi. Other words, a double bond can move toward a double bond. And we have 2 double bonds here, don't we? We do. This particular type of setup, this is a conjugated system. The other 2 examples we did were isolated. They were isolated dienes. This is a conjugated diene. The reason? Double, single, double. Double, single, double. Double, single, double will get you in trouble if you're not careful. So what does that mean to me? What does that mean to this type of reaction? This is what it means, folks. Delocalization can go forward here, which means maybe this left-handed carbon, whichever way you want to go with it, it's the same on either side, so it doesn't really matter. This sp2 carbon here is located next door to another sp2 carbon. Delocalization can happen and can go forward. So that carbon decides to take one of these bonds and whoop, over to the other side it goes. Well, when it does that, this poor little carbon has been ripped of those electrons. There's no more for it. And because it's been stripped of electrons, it now becomes a positive charge. All right, well, this carbon, it's got 5 bonds now. It can't have that. We've already talked about this, right? So that carbon's going to have to make the decision to say, no, no, no. I'm going to stay at 4 bonds. So I've got to get rid of that extra bond that was there, and I've got to shove those electrons to that carbon there at the end, and that carbon's going to go, whoa, wait a minute, I've got extra electrons. I'm not supposed to have them, but I'll keep them just for a minute. And those extra electrons make it negative. All of a sudden, delocalization changes the structure. That was something that we never expected back in the day because we weren't looking for delocalization. The examples that we were giving you had nothing to do with delocalization. We made sure of that. But these things can happen. Delocalization can happen at any time. We just have to keep an eye out for it. And I think we're at a point now where we comfortably can look for these types of things, I hope. So if this molecule rearranges, look at what happens here. I get 2 new targets, don't I? I have a carbon that is positive, and I have a carbon that is negative. Folks, these are the new sites of reaction right there. So when this Cl2 comes in, the Cl will go onto one side, and the Cl will go onto the other side. And when that happens, well, that takes care of that negative, and that takes care of that positive. And this is our other product that we have. If I wanted to name this, what do I name it? Well, this is going to be a 1, 2, 3, 4. It's still a butene, but my double bond is on carbon number 2. Again, symmetrical, it doesn't matter which way you go with it. And then on carbon number 1 and on carbon number 4, I have the dichloro positions. 1,4-dichloro, 2-butene. That is the name of the structure. That is totally different than option 1. So this is the problem with delocalization. We need it to understand the rules first. Then we need it to do some examples about how to identify delocalization and how to kind of figure out how it changes the molecule structure. Because the double bonds get a little wiggly inside of that molecule. They start to move a little bit. And in this case now we see how this affects reactions, don't we? So again, 1 mole of Cl2 and DCM gives me option 1, where it goes on spot 1 and 2, pretty much. Or it also gives me option number 2. And that's because of delocalization that took place. The double bond rearrangement happens. 2 sites of new attachment open up, and that's where the incoming group would go. The same thing would happen if it was HBr. The same thing would happen if it was water and acid. The same thing would happen if it was alcohol and acid, folks. The same things go on. It's the same attachments that go on to these reactions that we've seen always, ever before. The difference is that I have to watch delocalization. Again, double, single, double, you'll be in trouble. That's what you got to remember. That's what I had to tell myself. And here I was sitting in my desk doing all of these organic tests, and I was probably mumbling that, and they were probably looking at me wondering what on earth I was talking about. Double, single, double gets me in trouble. Double, single, double gets me in trouble. And it will get you in trouble too if you're not careful. Because these are unexpected products that we have to include. We have to say that they're there. Okay, so let's look at another example. Let's take CH2, double bond, CH, single bond, CH, double bond, CH2, and then this time let's react this with HBr. 1 mole of it, 1 mole of HBr. Okay, well, this is a symmetrical molecule again, just to prove a point. Doesn't really matter which one you tackle. I'm just going to tackle the one on the left-hand side. If you go to the one on the right-hand side, you'll end up with the same product. It doesn't matter. So I'll redraw my reagent. I'll the double bond. I'll do 2 sites of attachment. H adds on to the side with the most H's. So that's going to go here, and a carbocation is going to get formed. So the carbocation is going to go there. There's no sense in it moving. It could if it needed to. Look at this. That carbon is a carbocation, and next door to that is a double bond. Huh. Uh-oh. Delocalization can matter here. That's something that I need to think about. So, on this carbocation, bromine could go at that spot. Whoopee! There's option number 1. Option number 2, though, I'm going to redraw the reagent because we just picked up on delocalization, didn't we? Yeah, we did. So if delocalization happens, folks, this carbon in the sp2 carbon has a neighbor that's also sp2. Double moves to double. So this carbon can decide to take that double bond and flip it over on the other side. And when it does that, poor little carbon to the left has just been ripped of all of those electrons and it becomes positive. All right. And then on the other side, well, that carbon's got 5 bonds, just like it did before. So it's got to make the decision to break one of those and shove them all the way down to that carbon. And this is what we end up with. This is a rearrangement that took place because of delocalization. Now we have a full-blown positive and a full-blown negative if it stays at this particular location. And it does. It will flip-flop back and forth. Remember, delocalized resonance forms. They always go back and forth all the time. Here's one of those examples. So we are adding H and we are adding Br. All right. So if this molecule splits up, H will go on and Br will go on. Folks, where do you think the hydrogen's going to go? Will it go to the positive or will it go to this negative one? It's going to go to that negative one because positive and negative opposites attract. So a hydrogen is going to go on first, and that satisfies that negative charge, so we don't have to worry about that anymore, right? And now I have this negative bromine, and this negative bromine is out there, and this negative bromine is going to look at this molecule and see that positive charge right there, and that negative bromine is going to go on to that spot. And that helps take care of that carbocation as well. Folks, these are 2 different products here. If I had to name them, 1, 2, 3, 4, this is a butene. Carbon 1 is the double bond. And carbon 3, I have a bromo group. Down here in spot 2, 1, 2, 3, 4, it's still a butene. This is happening at carbon number 2. And on carbon number 4, I have a bromo group. 3 bromo, 1 butene? Or 4 bromo, 2 butene? The top answer is what most people will get. They will get that one because they're not thinking double, single, double cause me trouble. Number 2 is sneaky. Delocalization changes the structure. Delocalization will go through and move the double bonds and give you a completely different structure than what you are accustomed of giving. We have a special term that goes along with these. Notice up here in the normal version, if that's what you want to call that, let's just say that I've numbered the molecules this way, or the carbons this way, 1, 2, 3, 4. We call this the 1-2 addition. The reason we call it the 1-2 addition is because it's the first and the second carbon in the double bond. The actual original double bond, the first and second one. We call that the 1-2 addition product. Down below, when this rearranges, notice the bromine actually went on here and the hydrogen went on here. This is not a 1-2 addition. This is called a 1-4 addition. And the reason is the first carbon in the conjugated system and the fourth carbon, 1, 2, 3, 4, are the ones that get targeted with the incoming groups. So when we do these reactions, when we predict these products, that's something that they're going to refer to. They're going to ask you to maybe provide the 1-2 addition product of blah, 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 blah. Or they're going to say, predict the 1-4 addition product of blah, 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 blah. And that is what they're referring to. The 1-4 addition is a trigger word. And that word is meaning delocalization, folks. 1-4 additions mean delocalization is going to happen. So you need to rearrange that molecule, rearrange that double bond, preferably, that's probably what's going to show up the most, and figure out what this maybe unsuspecting product is going to be. It is the key word for delocalization. All right, well, let's take a look here. This is another example. This example is 2,4-hexadiene. Notice this sp2 carbon is right beside of another sp2 carbon. So delocalization is going to happen in here, folks. So if they add Br2, okay, we're going to split this down the middle. If they add Br2, we're assuming 1 mole and that's it. This molecule is very symmetrical. There's no rhyme or reason. This double bond is as equal as the right-handed double bond. There's no difference in them. So the double bond is going to break. That's what you see here, single bond. And a side of attachment will open up there and there. That's bromine and bromine because we're adding Br2 with DCM. The other double bond doesn't get touched. It stays. We only have 1 mole of this. So nothing goes on at that alkene level. And this again is called a 1-2 addition because in the conjugated system, that's what they refer to it as. The conjugated system is actually this piece right in there. Okay? That's where the movement is going to happen. So at spot 1 and spot 2 of that delocalized system, we get an addition product, and that addition product is the addition of Br on one and Br on the other. But delocalization can go forward. So this carbon can decide to flip the bond over. That creates a charge here, which is positive for a carbon. And this carbon says, oh, I can't have 5. Carbon, you're going to have to take those extra electrons, and you become negative. So in this setup, we're still targeting carbon 1 and carbon 4 of that delocalized system. So we are forming a 1,4 addition product. Notice it's not the actual number of carbons. Okay? The actual number of carbons, that system is actually carbon 2, 3, 4, and 5. That is not what 1, 2, and 1, 4 stands for. 1, 2, and the 1, 4 only looks at that delocalized bracket. That's it. They could care less what else is outside of that bracket. I could have as many carbons as I want to have. It doesn't matter. That is not what the 1, 2, and 1, 4 addition stands for. 1, 2, and 1, 4 represents the first and second carbon of the conjugated bracket. And 1, 4, the first and the fourth carbon of the conjugated bracket. That's it. Because that is the definition of a conjugated diene. Double, single, double. So if it rearranges, the double bond goes in the center, 2 sites of attachment open up now, the spot 1 and the spot 4, and bromine goes on one, and bromine goes on the other. So we get a completely different product than what we would expect. Here's another example. This example, no conjugation. If I look at 1,4-hexadiene over to the left, folks, this 1,4-hexadiene, I mean, this is double, single, 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 double. There's not a conjugated system. Therefore, I do not have to worry with this whole concept of 1, 2, and 1, 4 addition products. That's only for conjugated systems. It's only for delocalized systems. So I look at this and I say, okay, is there a preferred treatment of one double bond over the other? It looks like I'm only going to add one HBr and that's it. Is there a preferred method? And the answer is no. This double bond is as equal as this one. It's a symmetrical molecule. There's no differences in them. You're going to get the right answer no matter which one you target, so who cares? So you break one of the double bonds, and they chose the one on the left. You see it gone over here on the product side. They add hydrogen onto the carbon with the most hydrogens. So Markovnikov reaction goes on. It goes on left. And then here, the bromine goes on to the carbocation that will not shift. So now let's talk fancy. I have reacted 1,4-hexadiene with hydrobromic acid. An electrophilic addition reaction has happened where the rules of Markovnikov have been followed. This isolated diene has targeted one of the double bonds. The double bond has broke. Hydrogen goes on to the carbon with the most hydrogens, forming a more stable carbocation, which is secondary. That secondary carbocation does not shift, because if it does, it goes to a secondary. There's no reason for it to do that. So that secondary carbocation stays in that position, and the bromide ion comes in and goes on to the secondary carbocation. And that satisfies the octet that the carbon needs, forming 5-bromo, 1-hexene. Look at that, folks. It's beautiful language. You know, I mean, all that you need there is to talk like that to someone and have a bottle of wine and some fine chocolates. And, folks, what can have a better night, right? Well, maybe not in your opinion. And honestly, not in my opinion either. But it shows you how far that you've came. From day one of starting the class, all of this continuously builds up over and over. And we have gotten to this point, and we've done it maybe very sneakingly. I've told you this before, and I'll keep telling you that over and over. So don't give up. Don't give up on this lecture material. Don't give up on organic. You're learning. You might not be getting it as good as you want. You might not be learning it as fast as you want. And that's okay. That's normal. It's organic chemistry, for goodness sakes. All right, so that's where we're going to stop. In the next video, we'll continue on with this concept of isolated dienes and conjugated dienes and delocalizations and 1,2 and 1,4 addition products. And we'll just keep trucking on until the end of the lecture, which is not too far away, by the way. Yeah, you heard it. Pretty short. I'll see you then.